turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists, the programme that brings you the latest breakthroughs in science, technology and medicine with me, Chris Smith.
And me, Will Tingle.
Now this week we're looking at the microplastics that are increasingly polluting the oceans and, together with their partners in crime, the so-called forever chemicals that cling to them, could be seriously harming our health and the environment. So how worried should we be and what can we do about the problem?
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Last month, a paper in the journal PNAS revealed that the average 1 litre plastic bottle of mineral water contains more than 250,000 tiny plastic particles bobbing about invisibly inside the liquid. But because they're made from hydrocarbons, other oily chemicals like to stick to them too, so these particles slowly gather up a cargo of compounds, including the plasticizers that are added to make the bottle flexible.
In the wider environment, this is happening on an even greater scale and involves an even broader repertoire of chemicals, including molecules called PFAS, polyfluorinated alkyl substances. These highly stable forever chemicals are widely used in industry and go into things like non-stick surfaces. But there's alarming evidence now that they are linked to health threats, including cancer and bone diseases, when they get into us, and wider damage to the ecosystem at large.
And the partnership and dual jeopardy presented by these forever chemicals and the microplastics they accumulate around is what we're going to consider today, starting with Anglia Ruskin University marine biologist Danny Green.
A microplastic is essentially, as the name would imply, a small piece of plastic. Now, there's been lots of different definitions, but the one that's generally accepted was defined by Hartman et al. In 2019 and a whole group of other scientists. And it is that it's pieces of plastic that are less than 1,000 micrometers, so less than 1 millimeter in size. This can include a range of different polymer types, and they can come from different places. They can either come already small, so primary microplastics, things like the microbeads in exfoliants, if you remember that kind of thing, and abrasive cleaners. But more commonly, microplastics are formed by the breakdown of larger items, and these are called secondary microplastics.
I do remember when I was doing my master's and someone came in to talk to us about microplastics, and a really striking representation of just how prescient they are, as they had a bottle of shampoo, a clear glass bottle, and said, this is the amount of microplastics in it. And it was maybe 40% of the capacity of the bottle was made up of these little things. Yes,
exactly, the microbeads. I mean, in the environment, the beads are actually very rare. I've only ever found, in my own research, one off the coast of Portugal somewhere, this little blue microbead. But the majority of microplastics that we find in the environment are different shapes, so fragments, films, fibres, car tyre particles, so little bits of car tyre that are broken off, and things like that. But yeah, there's a huge diversity of microplastic types.
We all hear the word plastic, but there's loads of different kinds of plastic. Presumably that means there's loads of different kinds of microplastics.
Yes, exactly, yeah. Lots of different types of plastics, different types of microplastics, lots of different additives that go into plastics, different coatings and things. So it does get very complicated trying to define them.
Crucially, though, none of them are good. Is that fair to say?
No, exactly. They're not something that we want in the environment or contaminating us either.
So to that end, how widespread are they?
Extremely. I mean, I'd be a lot more surprised if you could tell me somewhere they're not. We've found microplastics down the bottom of the Mariana Trench all the way up on Mount Everest. You know, not completely surprising because we've found plastic bags as well at the bottom of the Mariana Trench. You know, so we're finding big bits of plastic too. So of course there's going to be microplastics there. So microplastics are everywhere. They're in the air that we breathe. They're in the water that we drink. They're in a lot of foods that we eat. They're in organisms, macrofauna, fish, mammals, pretty much everything really.
That kind of implies then that we do end up interacting with them daily and quite a lot.
Yes, and there is evidence for that because we have found microplastics in human placenta, in feces, blood and other organs. I would note as well that there are some discrepancies between academics amongst the exact amount of microplastics because some of these studies didn't include very good quality controls. But it's not to say that there's disagreement that they are in humans, it's that we're disagreeing over how many there are. But yes, we are definitely interacting with them.
as a recent study came out, that there's 250,000 microplastic particles in every bottle of water. We are inevitably going to consume and ingest a fair amount of them. I mean, what's the worry with that? Is there a potential health harm?
There is potential health harm. It's difficult to tell at this stage because obviously you can't experiment on humans, right? We're not going to get ethical approval to do experiments to see exactly what the impacts are. But we do know from studies on animals and invertebrates that it can have effects on development and growth and general kind of health and immune responses even and things like that. So it's not a huge leap to say that there might be impacts on people. And there are some studies coming out from the medical profession that there's correlations between the size of babies that have been born and the amount of microplastics. But it's more correlation than causation at this stage. And I'd say we should be applying the precautionary principle anyway. We don't really need to wait and find out, do we?
Are the microplastics themselves the only concern? Obviously, we're concerned about them and they seem basically near ubiquitous at this point. But are they also enabling other harmful chemicals as well?
Yeah, so the interesting thing about plastics as a contaminant is that they're essentially a double-edged sword, or potentially triple-edged. You've got the physical contaminant, so the actual, solid piece of plastic itself, and then you've got this chemical contaminant. So you've got either persistent organic pollutants that they might absorb from the environment and then release, or the plasticizers and different chemicals that they're made with to begin, and these can also leach out. And then you've got the biological aspect of microbial communities living on them, which might also have an effect. So you've got this sort of triple-edged sword in one contaminant. There's also forever chemicals, of course, are a huge concern at the moment. These have been found in the environment and in organisms, in marine, freshwater, terrestrial, and in human foodstuffs and water as well.
Do they have a particular relationship to microplastics?
Yeah, so a lot of plastics, particularly food plastics, are made with these per- and polyfluorinated alkyl substances, or PFAS substances. These help to improve the function of the item by repelling water and oil. So they make the plastic function better, but there might be a negative consequence of that in terms of human health.
Danny Green. So, legislators, aware of the potential risks, do aim to keep these chemicals and risky plastics away from human food chains. But there's a problem. Because we're also eager to minimise damage to the environment by recycling plastic to the greatest extent possible, and although rules exist about what sorts of plastics can be recycled into what applications, a recent study by Birgit Goecker, a senior scientific officer at the Food Packaging Forum, highlighted that cross-contamination in the recycling process means that plastic materials that shouldn't be going anywhere near the human food system are nevertheless ending up there.
So if you use the recycled plastic in food packaging, for example, again, the source should be pretty clean. PET bottles should only be recycled into new PET bottles or other containers. However, there are cases where you find residues of your old TV in food packaging or similar materials. And that's for sure not intended and shouldn't be like this according to the law. There are several concerns. We don't know that these chemicals exist in these products. Additionally, of course, many of these chemicals have been tested and shouldn't be there. For example, there are carcinogens that cause cancer, that interact with the hormone system. These chemicals shouldn't be there.
Birgit Goecker there. PFAS compounds are so hardy and difficult to break down that they've earned the name forever chemicals. Historically, they were regarded as inert and harmless, but data have slowly accumulated to the contrary, some of it already collected and allegedly kept under wraps by the very companies making these substances. In one instance, their own scientists calculated that the safe levels of exposure were far lower than the accepted legal limits. Victims adversely affected did begin to come forward, but initially struggled to get their voices heard. Robert Billop is a US lawyer who took up their case and subsequently brought a class action lawsuit representing millions of exposed individuals.
This is an entire family of chemicals that are completely man-made. None of them existed on the planet prior to about the time of World War II. Some research as a result of the Manhattan Project, looking for a nuclear bomb, basically resulted in this new type of technology that companies were able to use, principally the 3M company in the United States, of being able to connect carbon and fluorine atoms together. That is something that really doesn't exist in nature. And so when you put these carbon and fluorine atoms together, it creates an incredibly strong chemical bond. It's something that's really useful in manufacturing, But that strong chemical bond also means that when those chemicals get out into the world, they don't break down under natural conditions. And when living things, including people, are exposed to those chemicals, our bodies really don't know how to get rid of these man made chemicals. So they stay there, they build up, and they persist for long periods of time. And unfortunately, we now know that they're incredibly toxic as well.
And their applications? Why are we making them?
Because they're incredibly useful. These chemicals are used to make materials waterproof, stain resistant, grease proof. You're talking about chemicals that have been used to help make things like non-stick surfaces, waterproof or stain resistant clothing, carpeting, things that are slippery like dental floss, even in things like firefighting foams or computer chips. Just an incredibly wide variety of uses for these types of man-made chemicals.
What was your association with them? How did you get involved in this story?
Well, I had actually got involved with this family of chemicals about 25 years ago. As a lawyer in the United States, I was working primarily with big chemical companies, helping them comply with all of our different environmental rules and laws about what can go into the air and water and soil. And I got a call one day back in 1998 by a gentleman who was raising cows in West Virginia, and his cows were getting sick after drinking white foam that was getting into the creek that they were using for their drinking water. And when we agreed to take that case on for this farmer, it was through the litigation and the lawsuit that we brought back in 1999 that allowed us to begin getting access to documents from the companies that were making these chemicals and using them. And that led to what became the next 20 to 25 years of nonstop court cases and litigation and court battles to get access to this information and documents. It was through that process of digging into these internal company documents that we found out that these chemicals even existed and how toxic they were. And most disturbingly, that the companies that had been making them knew how toxic and dangerous they were, but had actually been intentionally covering that up, withholding that information from scientists, regulators, and from the public.
The action that was then taken, it was a class action. You got lots and lots of people together who had all been impacted in some way. Is that how it played out? And the amount you won was north of £500 million, wasn't it?
The original case started off with just one family. Once we had figured out what was happening with the cows and with the exposures that family had, we ended up then bringing claims on behalf of the entire surrounding community, who we found out had the same chemical in their drinking water, some 70,000 people. And we did
This was
that
coming
through
from a local chemical company, was it?
Correct. This was exposure that was coming from a DuPont Teflon manufacturing plant along the Ohio River in the United States. We found out that the chemical PFOA that they were using to make the Teflon had gotten into their drinking water, some 70,000 people. So we pursued that case as a class action. We then ended up finding out the same chemical and related chemicals were used in other communities. We brought additional cases for others. And over the last 20 years, we have pursued that all over the United States. Now that we're finding out these chemicals are in drinking water all over the country, we are representing hundreds of cities, municipalities, over a dozen different states that are bringing claims for the same drinking water contamination and environmental contamination. And just last summer, we were able to reach settlements with 3M and DuPont, where they're now agreeing to pay up to over $13 billion to remove this from drinking water.
Presumably, this problem is not unique to the United States.
It is not. Over the years, as we scoured all these documents and really started to learn where these chemicals were used and all of the different products they've been used in, and what we've learned is these chemicals have made their way all over the planet. There's one product in particular that was very effective in getting these chemicals sprayed out all over the world, and that was a certain type of firefighting foam called aqueous film forming foam, or you may see it referred to as AFFF. And how are you told to use that foam? To spray it out all over the ground. And that foam historically has had PFAS, these chemicals in it in high concentrations. And although the companies making those chemicals knew that, that information wasn't shared with the firefighters, with the military personnel, or with anybody else. That this stuff, if you used it and sprayed it out all over the place, was going to put PFAS into the ground, into the water. So now we're finding these same chemicals in drinking water, in groundwater, in soil, all over the planet.
What's been the impact of your work on regulation? Are things now tightening up, presumably with potentially billion-dollar settlements looming over them? The manufacturers have had a rethink.
It's been an incredibly long, tedious process to get this story out to the world about the fact that these chemicals even exist, what types of products they've been used in, and the fact that what happened here in the United States, what started in West Virginia, these are the same chemicals that are now being found in the water in the UK, in Italy, in Australia, in Japan, that this is a global contamination story. It took a long time to get that information out. It took things like having to do a feature film like Dark Waters, or a documentary, The Devil We Know, or the book Exposure, to help get the public to understand what had happened and the fact that it's the same chemicals now that are being found everywhere. But once that story finally came out, and we saw that particularly the last couple of years with these films and book, we saw the power of that information. Lawmakers started proposing changes to the laws in the way we handle these chemicals. The public started demanding that companies take these chemicals out of their products. And so now we're seeing changes not only across the United States in the laws, in the regulations, but globally as well. The EU proposing a potential ban on all of these chemicals. And even the original manufacturer, 3M, coming out and saying, finally, that it will agree to stop making any of these chemicals by 2025.
Interesting story, isn't it? Robert Billett there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith.
And me, Will Tingle. Still to come, what, if anything, can we do about forever chemicals? The evidence base for the health risks associated with PFAS is strengthening. Last year, it was found that exposing cancer cells to certain forever chemicals causes an increase in cell motility, making them more likely to metastasize. Also, a study from the Keck School of Medicine found that PFAS accumulation in adolescents may limit their peak bone mass, leading to greater risk of osteoporosis later in life. And there's growing concern that PFAS exposure can decrease fertility by interfering with hormone signalling. At the moment, though, the real limit to our knowledge is time. The majority of PFAS health studies are still in their early stages, so we haven't had enough time to see their full effects or discover the mechanisms of these actions. We also don't know where the cutoff in dangerous doses is and how it differs among different groups of people.
So time will, as they say, inevitably tell. Well, let's return now to the other focus of the programme, the billions of plastic particles that are accumulating in the environment year on year, which are soaking up and concentrating these forever chemicals and helping them to move around the planet and potentially get into the food chain. These plastics themselves also pose a direct health impact on a range of marine species. Richard Thompson works at the University of Plymouth, and he has a special attachment to this subject because 20 years ago he coined the term microplastic, and he's been working on the problem ever since.
We got evidence from quite early work that when you had 1% of plastic, it was PVC in this case, mixed with 99% beach sand that wasn't contaminated, that affected the ability of marine worms to get goodness from their food, to put on weight in the normal way, if you like. And that might seem slightly trivial, but of course that's not killing them, but it's affecting them over their lifetime. That could potentially affect their growth, their reproductive output. And I think that points to where probably the greatest concern in my mind about these small bits of plastic is. It's not that they're going to poison all of the marine life overnight. It's more these long-term chronic effects where you might see consequences over a lifetime. Of course, at higher doses, we see more immediate effects. We've recently been working with tire particles, for instance, which it's clear when you have to replace tires, they've lost quite a lot of tread, right? Well, all of that material is going into the environment, and then we've got small pieces that have a range of chemicals in them that are potentially of concern, and they can be entering in quite high quantities near to roadways where they will wash off when it rains heavily.
And these forever chemicals, they're presumably also part of the potential toxic cocktail that can stick to particles and then get into plastic particles and then get into all species across the different elements of the trophic levels you mentioned in this way.
That's right. And I think as we consider those, we need to consider the two possible pathways. Now, one is the plastic in water has acquired those chemicals from the environment. The forever chemicals are already there, if you like, from other sources. Many of these chemicals are hydrophobic in nature, so they will latch onto the surface of plastic. And that is quite a significant effect. In a matter of days, plastics can concentrate some of these chemicals orders of magnitude more than the concentration in the surrounding seawater. And some of the early work we did showed that when a creature ate those particles, it increased the rate of release of those chemicals. So you potentially got a mechanism of transfer. The rate of release into warm-blooded creature was up to 30 times greater, let's say, than if we transferred our piece of plastic with the chemical burden just back into clean seawater. So there's a mechanism there, but even that doesn't prove harm in itself. It establishes a mechanism. And there's subsequent work that we did, because of course, if you picture a creature in a contaminated ocean, it's acquiring those chemicals directly from seawater or from the food that it eats, as well as from the plastic. So the key question really with respect to this, the issue of transfer of chemicals by plastics is how much worse does the presence of the plastic make it for that creature? Okay. And with the chemicals that are already in the environment, probably the additional contribution of the plastic is quite small compared, let's say, to picturing a fish or a filter feeding mollusk taking the seawater over its gills and acquiring the chemical directly that way, because it's passing far much more water over its gills than it is encountering plastic. Those studies were based, and this is the caveat that I think is going to be interesting going forward, they were based on assuming the plastic passes through the gut in a normal transit time. It goes in and it goes out, how much chemical could be released. Now, since then, we've shown that the nano-sized particles of plastic litter will very rapidly circulate throughout all the tissues in the body. We used scallops of marine mollusk, and we showed that within 6 hours, they'd passed from being ingested throughout the circulatory system to all of the tissues. But weeks later, some of those nanoplastic particles were still present in the scallop. And so I think in those scenarios, there may be different potential for harm where you've got bits of plastic with a chemical burden lodging in specific tissues. So I think that the question about chemical transfer from water to creatures by plastic, there are also additive chemicals that are used at the time of manufacture. That's a slightly different pathway in that because these are additives in the plastic, they're additions to the environment when the plastic enters the environment. So it's a different story to the plastic picking up a chemical burden that's already in the ocean and redistributing it. And you're asking the question, did the plastic make things worse with respect to that chemical that was already there? If you're talking about the plastic bringing a chemical into the environment with it, then it's clearly an addition to the environment. And some of those chemical additives can be present in the plastic product at really high concentrations, at higher doses, if you like, than you would likely to accumulate onto the plastic from seawater.
Could the plastics paradoxically be helpful in some respects? Because if they are good at sucking up the nasties, and we'll put to one side the nasties that they might bring with them because they're oily, and the oily chemicals would rather be on the plastic than in the seawater. If you put plastic in the water and it soaks up all these things and then sinks, does that mean actually the plastics might be helping to a certain extent to get rid of some of these forever chemicals or these other nasties that would otherwise end up in a fish?
I wouldn't see it or describe it like that. Certainly, we can use plastics to mop up oil spills because of this affinity. So you can use them in a cleaning sense, but I certainly wouldn't think about putting plastics into the ocean to accumulate some of these chemicals. And it's all really about thinking about the kind of concentration gradient between the amount of chemical that's in the water, the affinity to the plastic, and the plastic can, of course, move around. If it sinks to the seabed, it's moving to a different compartment. And if there's a lower concentration of that forever chemical on the seabed compared to at the sea surface, then some of it will be released again. And one thing that is very different about plastics, in the same way that the oceans have the ability to move around particles of natural sediment, it can do the same with plastic particles. So they don't become diluted and diluted and diluted. They can become redistributed and reconcentrated in some location.
And to finish, how worried are you about these forever chemicals, these various industrial substances which are pretty pervasive and appear to hang around for really long periods of time and are getting into the sea? How bothered are you by that?
I'm very concerned about anything that we're putting into the environment that is, persistent. There's evidence of toxicity, and it's potentially going to accumulate. And I think this has to be the way forward, that we have to look at and screen in a much more responsible way the chemicals and the particulates that are entering the environment in order to make sure that we're not creating long-term effects. Because once these plastics are micro and nanoplastics, there's no way of removing them. And it's a similar scenario with the forever chemicals that you're talking about.
Poignantly said. Richard Thompson there.
So, how do we solve this problem? Is there any way of taking the forever out of forever chemicals? Well, Chemistry World's Philip Broadwith took me through some of the ways people are trying to deal with the problematic PFAS.
From my point of view, the best thing to do would be to prevent them getting out into the environment in the first place. The most effective way to do that is through regulation. Beyond that, we know there's going to be some emissions. We know there already have been some emissions. So there is PFAS in the environment. We need to start to treat that. The best time to treat it is at its source. There's relatively available filtration technology that companies that produce PFAS could add to their water treatment, and the sort of water treatment works could add additionally to the things that they're already doing. Part of the problem with filtration is it's not particularly effective. You'd have to have extra different filters to what you would normally have for other contaminants, which is an extra expense. So people are reluctant to do it unless they have to. And also, if you filter out the PFAS from the water, you've still got PFAS there to deal with, either on your filtration material or in a separate waste stream. So it still needs to be destroyed in some way. And that's where we get to the difficult part.
There do seem to be quite a few pretty out there looking schemes in order to tackle these particular chemicals as well.
Yeah, and the problem with destroying these things is that they're really, really stable. The carbon-fluorine bonds are really, really strong. That's one of the things that gives them their really useful chemistry, but it also makes them really difficult to get rid of. There are a few ways where you can destroy certain types of PFAS. You can treat them with light to try and oxidize them, try and break those carbon-fluorine bonds. There's people doing electrochemistry, so you have an electrode, then you pass electricity through the molecules to try and break them down. Even people using high-energy electron beams from particle accelerators. That gives you an idea of how difficult this is to break these molecules down. Part of the problem is most of these ways will break down some types of PFAS, but because PFAS is a big family of compounds, lots of different compounds with slightly different properties, they all break down in slightly different ways. One of the most effective ways is to use what's called supercritical water oxidation. That's when we take water and heat it up to relatively high temperature and high pressure, and we lose the distinction between a liquid and a vapor or a gas, which is this state called supercritical, and then that makes highly oxidative environment that can break down quite a lot of different types of PFAS. But that technology is very much in its infancy. It also takes quite a lot of energy and it's expensive and that kind of thing. So it's doable, but it's hard.
From what you're describing, it does seem like for the moment we're going to be fairly stuck with these.
Yeah, and that's why prevention is going to be the best long-term strategy. But the problem is we already have quite a lot of this stuff out in the environment. It's already contaminating various sites, particularly military and airport type sites where they use a lot of the firefighting foams that have certain types of PFAS in them, and around industrial emissions, historical industrial emissions into rivers and that kind of thing. There's a few court cases going on in the US around those. So we know it's already out in the environment. So how do we treat that? That becomes even more difficult because you then have it in soil, you have it in waterways, you have it in all sorts of different environments, it's very difficult to do a lot of these high energy, expensive techniques. So there are people looking at kind of microbial or biological ways of breaking down PFAS, developing enzymes that will break down the carbon fluorine bonds, which you could then start to maybe apply in the environment. And that starts to become a way of clearing up the emissions that are already there. But again, there's a lot of things to kind of work out before you can start putting that kind of thing just out into the environment as well.
Throughout all of these interviews and forays into forever chemicals, the word that keeps cropping up is uncertainty of the true effects on people and the planet. And it feels justified because the real lack of long-term knowledge of this tiny, omnipresent set of chemicals is, well, to me, the most concerning aspect of this. Are you also concerned?
Yes, uncertainty is exactly why. It's probably true that the ecosystems of our bodies and of the environment can handle a certain amount of these without too much of a significant effect. But the problem is that they are so persistent. They stick around for so long, and they will therefore accumulate unless we do something to stop them being emitted into the environment. And we don't know what the really long-term effects are, and we don't know how much we can take. We may already be beyond the level that is acceptable. Certainly in some places, we know that we are. So that's the thing that worries me.
Chemistry World's Philip Broadwit there. Well, that's where we have to leave it for this week, but do join us next time when our focus will be on the roads of the future, including detailing the latest technology driving us towards a pothole-free tarmac surface. Wouldn't that be lovely? And also automatic road repair services. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith.
And I'm Will Tingle.
And from both of us, and from everyone here at The Naked Scientist, thanks for listening, and until next time, goodbye.